Hello everyone and welcome to this Unisense workshop. This one will be focused on biogeochemistry. We've previously held these workshops but in a more general way, but this time we'll try to focus more on one subject. Yeah, okay. So this workshop will consist of 5 parts. Today I will give 2 lectures, one about how microsensors work and what they can be used for, and what to think about when using them. I will give one more lecture then about lab-based studies. Tomorrow I'll give a lecture about how to use our system for field and in situ studies. And then I will do 2 demonstrations tomorrow. One will be a demonstration of a field microprofiling system and how to use that with our software to measure profiles in a sediment core. And I will at the end tomorrow also do a demonstration of our software and how to use that to do activity calculations, so to do these diffusion calculations within the software to get rates and fluxes and so on. So just a short presentation for myself. I have a PhD in biogeochemistry microbiology, and I'm application scientist at Unisense. I've been that for 4 years. Previously, I've worked for more than 25 years at the National Environmental Research Institute in Aarhus University in Denmark, working mainly on the marine nitrogen and carbon cycling with focus on microbiology and biogeochemistry. So the outline for the presentation now is I'll present Unisense briefly to those of you who don't know Unisense. Mention something about sensor production. Then I'll go in detail with the amperometric microsensors. I will go very much in detail with the oxygen sensors, and then less detail with the other sensors. Then I'll talk about the potentiometric microelectrodes, the optote for oxygen, and then we can do a lot of adaptations and customizations of our sensors to fit the exact need you have, and I will talk a bit about that. Then something about the importance of tip size of the sensors. We make sensors in many different sizes, and there's a good reason for that. And then at the end also something about calibration, which is also necessary. Unisense was established in 1998 by scientists from Aarhus University that wanted to commercialize the microsensors. Still largely owned by scientists. We are now 23 employees at the moment, and we have more than 20 years of experience in developing and constructing and applying microsensors and all the electronics and software that go with it. We are an ISO certified company, so we have control of what we are doing. You can learn more about us on our website. We are located in this building in Aarhus in Denmark. We sell from Aarhus actually to most of the world. We have a network of more than 5,000 customers, and we also have distributors in some countries, those where it's too difficult for people to handle the import themselves mainly. We do physical workshops. The online workshops is a Corona thing. We may continue doing it though, but we didn't do it before the Corona. Before that, we had always 2 annual workshops in Denmark every year, where 15 to 25 people come to Unisense, some with their own samples, some just to learn, and they get a chance to play around with our sensors and systems in general. We also do a workshop in China every year. We will do again soon, I hope. And we always train our customers that buy the advanced field systems as well. We have more than 1,000 guests now for training, instructions, workshops, and so on. We write a lot of emails every day, and you are welcome to ask questions or get quotes or whatever you want. We answer within 1 working day always. Our sensors give data that can be published, and at the moment, we have more than 2,500 peer-reviewed publications that have been, where data have been obtained with our sensors and equipment. So these are pictures from the building here where we've had workshops. The last one we had a couple of years ago, where people walk around and play around with our systems and their samples. That's normally a lot of fun. We hope to be able to do it this late spring, early summer again, but who knows at the moment. So before I go into detail with how the sensors work, I'll just give a couple of examples of what they can be used for and why you should use them. Well, first of all, most people use them because they are small. So you can get a very high spatial resolution and measure things you couldn't do in other ways. They are also very non-destructive, minimally invasive, so you can measure chemical gradients in the same spot several times without actually disturbing them. They're very fast responding, which also gives a lot of advantages, as you will see in some of the data I will show. They give real-time data, so you can see what you are measuring all the time. There's always a real-time signal. They have very low analyte consumption, which also leads to a very low steering sensitivity, and that's really handy. And I will mention that in a moment as well in more detail. Just a couple of examples where the sensors have been used. For example, in microbial mats, either in the lab in sediment cores here or in Yellowstone out in the field. Just an example of what you can get. The depth axis is always vertical here. That's the x-axis, and the concentrations are given on the y-axis, which is always horizontal. As you see here, oxygen was measured, had a peak here at about 0.4 millimeters depth, and then went to 0. Sulfide came up and reached almost the bottom of the oxygen zone. There was a high peak of in pH here created by the CO2 consumption by the photosynthesis here, producing the oxygen and so on. Another example where the system had been taken to the field, there was an Arctic lake in Canada, I believe, where the field microprofiling system was brought out and cores were sampled in this lake. They were interested in looking at the effect of glacial input on sediment biogeochemistry in general. 2 stations with high glacial input, 2 stations with low glacial input, and 1 station without any glacial input. It was very clear effect on the oxygen signal here. So oxygen went to 0 already a couple of millimeters in the sediment when there was high glacial input. The low glacial inputs are the 2 gray curves here, and oxygen went significantly deeper into the sediment as there was a lower oxygen consumption. And the one that was not affected by glacial input, there was even half of the oxygen present at 60 millimeters depth. All the same signal on the redox potential here. So redox potential was negative, very negative here in those affected by the glacial input, whereas the others was not so much, and pH also had an effect. But that was just a couple of examples for why you should use microsensors. So you can take the sensors out to the field. This was to a field station in the Arctic, but you can also take them underwater, and I will spend some time on that tomorrow. There's a whole presentation about what the sensors can do for you in situ, either from mini profiling and all at shallow waters or into the deep sea to 6 kilometers water depth on a free-falling lander. All the microsensors, they start out as a glass tube that has been heated in a gas flame and then pulled so it gets thinner. To get it even thinner, it's mounted vertically, and in an electrical heating loop, and then the gravity pulls the tube down, and the final shape of the tip here is created by an even smaller electrical heating loop under the microscope, so you can get the tip size and so on exactly as you want it. Then once you have the casing, then you put a cathode to the inside. Everything is now made under the microscope because it needs to be very precise. Then it's glued together, and finally cables are mounted so they are ready to be plugged into an amplifier. So the basic microsensor starts out like this. So it's a plastic shaft, the glass tube, and then here it has been heated and pulled, so it becomes thinner and thinner all the way out to the tip. The tip for standard sensors come between 10 and 500 micrometers. We can go lower and make them down to 3 to 5 for some of the sensors. That's mainly for very special applications. Each sensor will need an amplifier. We have a number of different ones. I will get back to that. And the amplifier needs a Windows PC running our software, so we can calibrate the sensors, collect the data, see the data in real time, and so on. This standard microsensor, basic microsensor, can be modified in many ways, and we have a number of different standard ways of doing that as shown here. So we can mount a needle on the sensor, so the tip sits here in the opening of the needle and is a bit more protected than when it was out in the free. We have a piercing needle version where the longer shaft is used, so and a thicker needle that is glued into the shaft, so you can actually pierce rubber septa with it and measure inside bottles or whatever you want. There's a stainless steel protection cap that will protect the tip if you're working in bulk waters. We have 3 different types of flow cells. You can mount the system in a flow cell, or you can inject very small volumes of sample into a flow cell and measure for that. The in situ connector is the one that's used for the in situ instruments, so taking it to the deep sea, and with that one you can go to 6 kilometers water depth. Microrespiration system, which I will touch upon later, where the sensor sits in this blue guide that allows you to get the sensor tip into a very small respiration chamber and measure changes in concentration in there. And then there's the steel tube, where the sensor sits in the opening of the steel tube here, and it's a stable sensor that can be used in many applications. Modify these sensors, the characteristics of them, so we can modify response time, we can modify steering sensitivity, and also the concentration ranges. And we can do a lot of other things. For example, just an example here, fluorescent solution had been added to the electrolyte of a microsensor so that it would be visible in UV light under the microscope. But that's, we can do many other things depending on what people need. So we have many different types of microsensors. Basically, we have the amperometric microsensor, those that produce an electrical current as a signal in the picoamp range, 10 to the minus 12th amp, that is. It's also called a Clark sensor. It's all our gas sensors, actually, oxygen, nitrous oxide, and so on. And when I say gas sensors, that means that they are measuring gases, but they will be able to do it both in liquid and in gas phases. Then we have the potentiometric microelectrodes, which could be, for example, a pH electrode. They all require a reference electrode to work, and the tips of the 2 electrodes must be in the same solution and be in contact, electrical contact with each other in that way. Then we have the microelectrodes, where the fluorophore is attached to an optical fiber and excited with light, and this fluorophore gives fluorescence, which is depending on the oxygen concentration. More detail about the amperometric sensors. We have these oxygen, sulfide, nitrous oxide, nitric oxide, hydrogen, and the stock sensor, which is a very which is an oxygen sensor with a very low detection limit. We have potentiometric sensors. We have these 3: the pH, the redox potential, and electric potential sensor. Then the optical microsensor, we have so far only the optode, the oxygen sensor for that. The oxygen optode. We have temperature microsensors and macrosensors, and also microsensors for diffusivity and flow. I will start out with the principle of an oxygen sensor, show you how that works in detail, and why use microsensors, what the advantages are, and then I will continue with the other sensors after that. So an oxygen sensor could look like this, with a very small tip. If you look at it sort of in a schematic drawing, there will be a glass casing on the outside, so a glass capillary, that's the thin tip. The opening is closed here with a silicone rubber membrane, which is very permeable to gases, so all gases will pass freely through here and get into the interior of this sensor. Same time, all ions will be excluded, so we have a chemically protected and also electrically protected environment inside where we can do the electrochemistry. The sensor has a cathode in the center here. It's a platinum wire coated with glass for electrical insulation, and then exposed at the tip with a piece of gold on here. It's charged negatively at minus 0.8 volts relative to a reference electrode sitting further back in the sensor. And there's an electrolyte inside, and there's a guard cathode. The function of the guard cathode is that such electrolyte will always contain oxygen, so when you switch it on, then this guard cathode, which is also negatively charged, will consume the oxygen here. And after a while, you'll get a very stable signal from the cathode, and it will only react to oxygen coming in from the outside. And that's what you want for such a sensor. And this sensor must be connected to an amplifier that has a picoamp meter built in, so it can measure this weak current, but it must also be able to polarize the sensor at the same time. And that's what these sensors, these amplifiers do very well. The electrochemistry inside this sensor is that when oxygen touches the gold surface, this is what happens at the cathode. That is that oxygen becomes reduced. It receives electrons and is turned into hydroxyl ions. Up at the anode part, the reference electrodes, silver is oxidized to silver ions and electrons, and the electrons flow through the cables and the picoamp meter down to the cathode. And this electron flow is the electrical current that we measure, which is the signal for oxygen. Polarize such a sensor. I said we polarize at minus 800 millivolts. This is here. Then if you have a sensor in air and you start from 0 and increasing the polarization, you see the signal is increasing until a certain level when it's constant over time. And then at the end here up, it will start increasing. If it's in the absence of oxygen, you will have a stable signal all the way up to around here where it starts to increase. Up here, water starts to become split into oxygen and hydrogen. That gives a signal. We don't want that. So that's why we stay down at 800 millivolts. In this range here, where you have the flat curve up here, the signal versus oxygen concentration is linear. We polarize up at 800, so we have a high capacity for reduction of oxygen. And that actually means that an oxygen sensor is linear all the way up to pure oxygen and even pressurized pure oxygen. So it can give a very high signal, measure high concentrations. As I mentioned, the electrolyte in a sensor will contain some oxygen. So when you connect a fresh sensor to an amplifier, you will see something similar to this. So you'll see a high signal right after it's being connected, and then it decreases over time as the oxygen content of the electrolyte decreases. And after 1 to 2 hours, the signal has become stable. So we always recommend that you switch the sensor on at least a couple of hours before you need to use it. And if possible, do it the day before. The lifetime of the sensor is not depending on whether it's being polarized or just lying on the shelf. So, but a long pre-polarization will give a very stable sensor. So polarize early. What is the reason for using the microsensor? As already mentioned, many people use them because of the high spatial resolution. They are small and you can measure many times without destroying your sample. And they consume very little analyte. One of my colleagues did this calculation. How long time will it take for an oxygen sensor with a standard signal of about 100 picoamp to remove all the oxygen that is present in 1 milliliter of seawater? And that was actually 34 years. And this means that for all practical purposes, the consumption of oxygen by the sensor can be ignored. But this low oxygen consumption is actually also the reason that there's a low sensitivity to steering for microsensor. That means there's a very little difference in signal between steered and stagnant medium. If you look at a macrosensor, in a steered environment and stop steering, then you will see a decrease in signal over time. And when you start steering again, the signal will come up. The reason for this is that the macrosensor will consume oxygen in front of the sensor and therefore lower the concentration where it is measuring. So it will keep lowering and lowering the concentration until it gets more or less stable after a long time. When you do the same with a microsensor, you don't see this, except if you look very carefully. You can see here there is a change of about 1% here, and our microsensors typically have a sensitivity to steering of 1 to 2% or so. We can make them almost without sensitivity. We also make them more steering sensitive. Depends on the sensor response time and sensitivity. They are fast responding, and typically when we talk about response times, we define talk about the 90% response. That is the time it takes for a sensor to give 90% of the full response. For example, here's a sensor sitting in air and then being put into an anoxic solution. And the signal decreases very fast and reaches the 90% response already after less than 0.1 second. This is a really fast sensor. Normally, our fast sensors have a 90% response time of, we say, less than 0.3 seconds or something in the range here. Standard sensors, oxygen sensors, for example, would have a 90% response time of 3 to 5 seconds or so. And then they are pressure tolerant if they are mounted correctly in the in situ connector here at the in situ amplifier. Then you can take them all the way to the deep sea, at least 6 kilometers depth. So summary, the oxygen sense is amperometric. We go from 3 to 500 micrometer and needle versions as well. We go from very fast to normal sensors, steering sensitivity low. They have a temperature sensitivity. All our sensors and all other sensors have a sensitivity to temperature, and we can compensate for that. I'll get back to that at the end of the presentation. All our oxygen sensors and also all the other gas sensors, they have a linear response, so we can get away with doing a 2-point calibration. For the oxygen sensor, that will typically be air saturation and 0. And they come in both lab and in situ versions. I'll now go through the other types of sensors. We have the sulfide sensor here. Similar construction, so there's the outer capillary, the blue here, the glass. There's a silicone rubber membrane in the tip where gases can diffuse in, and you can see this is H2S that can diffuse in. That means that we will only measure the H2S, not the HS minus and S2 minus. In this case, this is a platinum anode, so it's polarized positively relative to the reference electrode, so that sulfide can become oxidized. We have two types, the sulf and the H2S type. I'll just mention those. The sulf type principle is that sulfide is oxidized all the way to sulfate, so you have an 8-electron process. The H2S type, that's only a 2-electron process because sulfide is oxidized to elemental sulfur only. And an iron cyanide complex is a mediator in this. Reason for having two types is that, well, this is the better sensor, but it has a sensitivity to hydrogen. So if there's hydrogen, significant amounts of hydrogen in the environment, we recommend using the H2S type instead. That one is sensitive to light, but the outer casing is painted black to avoid light getting in and interfering. So, but still, out in strong sunlight, it may be much better to use the other one. This sulfide sensor, as I mentioned, measures only H2S, and that is in equilibrium, a pH-dependent equilibrium between with HS minus and S2 minus. And you can see those here. So the red is H2S, and that is dominant at lower pH, whereas S2 minus is dominant at higher pH. The implications of this is first for the calibration, that if you do a calibration standard from stock solutions, so creating a concentration of sodium sulfide or zinc sulfide as we do in our calibration kits, then you should make sure to have a pH less than 4, because that means that will more than 99% of the sulfide be in the H2S form, so you know the exact concentration. If you're up here, you don't know how big a part of your sulfide that is actually in the H2S form. This also means that when you do measurements out in your samples, you must calculate total sulfide because it's not measured, it's the H2S that is measured. And to do that, you need to know the pH value. If you know the pH value shown here, it's H3O plus, and the H2S concentration, you can calculate the total sulfide concentration. For that, you need these constants that you can find in the literature and also in the manual, I believe. They are depending on temperature and salinity. K1 is relatively well determined. People agree on the value of that, whereas K2, there's some deviation in the literature for that, but you can actually get away if you're below pH of 9 or so, you don't need to take that into account. You can actually do the calculation with the K1 only. So the salt type sensor, that is linear, up to 300 micromolar in the standard version. It can go up to 500 micromolar, but then it's not linear at that range. We can make special versions, high range, up to 10 millimolar, and also low range that has a detection limit of all the way down to 3 nanomolar. It has a lifetime of about 6 to 12 months, steering sensitivity like the others of about 2%. It's temperature sensitive at 1 to 3% per degree, just as the others. And you need pH to calculate the sulfide, and the response time is about 10 seconds. The nitrous oxide sensor is a bit different from the others. You see here it's standard, more or less like an oxygen sensor, but it's placed inside this ascorbate chamber. If you look at the tip, you can see the sensor sitting here with the blue outer casing the glass, and this is the ascorbate chamber. The reason for that is that this cathode would measure both oxygen and nitrous oxide if it was getting in there. The ascorbate is able to remove oxygen, so when a mixture of oxygen and nitrous oxide enters through the silicone membrane in the front, oxygen will be removed here before nitrous oxide is then measured inside. See a microscope photo of it here. You can see the foremost silicone rubber membrane here, the ascorbate solution here, and other silicone membrane, the one belongs to the sensor, and the cathode here. We also do a more sturdy version of this for wastewater treatment plants, where the glass walls are thicker and the membranes are a bit thicker. It has a bit longer lifetime and slower response. So the characteristics of this is it's a very stable sensor. It has a wide range. It can measure up to 500 micromolar in the standard version, but we can make ones going up to 28 millimolar, that is pure nitrous oxide. And we can get them as sensitive as down to 25 nanomolar in detection limit. The expected lifetime for such sensors is 4 to 6 months. They require pre-polarization because the surface on the cathode must be activated before it can be used. The response time is a bit longer than on the other sensors because it has a longer distance from the outside into the cathode. It's very specific. The only interference is NO, but that is normally not present in significant concentration unless you add it in experiments, but then you know it's there. It's not sensitive to steering, and it has the same temperature response as all the other sensors. Nitric oxide sensor. That is a bit different from the others in that the anode here is made from a carbon fiber. It has a very thin silicone rubber membrane at the tip and then a glass casing on. And NO can diffuse in through the silicone rubber membrane. It's a very sensitive sensor because it has a detection limit down to 3 nanomolar for the bigger ones. And the reason for that is that, as I mentioned, NO is always present in very low concentration, if at all. It has a very short membrane, and that means you must use grounding so you don't have differences in potential between the inside and the outside. If you have static electricity, there may be generated a spark through this silicone rubber membrane, which will destroy it. Calibration is a little bit difficult, not because of the sensor, but because NO is an unstable molecule. It requires some polarization time to get stable, very fast responding, down to 1 second, and works only in the lower range, unless, of course, we modify it, we can do that. And it's very sensitive to steering because of this very high sensitivity. It also comes in the same versions, more or less, like all the other sensors. We also have sensors for hydrogen. We have 2 different versions that are very similar. There's the standard version here, and then there's the H2X version here, which is not sensitive to hydrogen sulfide. That one is sensitive to hydrogen sulfide. It is very similar in construction to the N2O sensor, that it has this extra chamber placed on top of the and in front of the hydrogen sensor, which removes the sulfide. So the 2 sensors are very similar. Hydrogen is oxidized on a metal surface here inside the sensor. linear response for the standard range up to 800 micromolar and a detection limit of 0.3 micromolar. We can get down to 50 nanomolar in the low range version, and the temperature sensitivity just as the others. Expected lifetime more than 12 months, response less than 10 seconds, and the H2S interferes. The H2X sensor, the X is the same as the H2 sensor, except that, well, there's no H2S interference. It has a longer response time and a slightly shorter expected lifetime. Such amperometric sensors, they require an amplifier. We have different versions to choose from. We have the lab type amplifiers here, the Uniamp series. This is a multi-channel one, which has channels for both the amperometric and potentiometric ones, and in addition, it also has an optical oxygen sensor channel. And we have dedicated amplifiers for one type of sensor only. This is a hydrogen Uniamp sensor. We have the field microsensor multimeter, which is the one that is splash proof. It is battery powered and can be taken to the field in the rain and so on. And then we have the in situ Uniamp, where you mount sensors you want to use with the in situ equipment. So the potentiometric microelectrodes, well, we have three of them: pH, redox, and electric potential. All of these require an external reference electrode. It can be the robust one for lab use, the micro for lab use, or the in situ one, in situ use, of course. The pH electrode is very similar to what other conventional pH electrodes you have in the lab. It's just smaller. It's made from a piece of pH sensitive glass that is melted onto a lead glass shaft and then filled with an electrolyte inside. The lead glass is very highly electrically insulating, so you can measure the potential of the pH glass. There's a picture of how a pH electrode would look under the microscope. This is a 50 micrometer tip diameter and about 200 micrometers long. The construction of this means that it does not measure nearly as much point measurements as the amperometric sensor. This has a certain distance, so about 200. You can get down for the thinnest ones to about 50 micrometer in length. Yeah, that's what it says here. That's all. The spatial resolution can go down to 50 to 100 micrometer. You need external references. They're excellent for biofilms, sediments, tissues, and whatever you want to work in. And they are needed for calculations of the total sulfide. For example, if you measure in profiles in sediment, you'll need both the profile of H2S and of pH to calculate the total sulfide. The redox potential electrode, that's basically just an exposed piece of platinum wire. You can see it here, melted into glass for electrical insulation. So it's only measuring out here. Simple electrode, also the cheapest one we have. It will always give you the difference in potential between this tip and your reference electrode. But typically you want to report this redox potential relative to a standard hydrogen electrode and not your calomel or whatever electrode you're using. So therefore you must calibrate it, but that's a very simple operation. There are some things to think about when using this. Even though it's a platinum surface, it can be contaminated, for example, by proteins or by hydrogen sulfide or whatever. So it should be cleaned now and then. There are procedures for that. So if you're in very reactive sediments, so with high sulfide concentrations, you should think of cleaning it regularly. And you should always check your calibration now and then to see that it's still measuring correctly, and make several profiles so you know what you are getting. So as I mentioned, we can make sensors in many different diameters, tip diameters. And the Clark type sensors, it's actually only the thickness of the glass wall that changes. Show the examples here. So this could be a 10 micrometer sensor, and this could be, for example, a 100 micrometer sensor roughly. The area of the sensors are the same, the membrane are the same, and the diameter of the opening in the sensor is this. We're getting the same flux of oxygen in, you're getting the same signal. The only difference is that you have a much thicker glass wall here than you have here, and therefore a more robust sensor. But you should not always go for the thicker ones if you want to be safe, because that has also some implications for the profiles you are measuring. I will get back to that later. So always use the thinnest one you can without breaking it all the time, of course. So I'll just mention a little bit about our microelectrode system. It's as I mentioned, it's based on a fluorescent dye that is sensitive to oxygen. It's fast responding. It has an EEPROM, so it has a serial number and calibration stored on it. It comes normally in this retractable needle design, but we also have this now with the 3mm steel tube where this sensitive dye is placed in the tip. It requires a microelectrode meter. We have a dedicated electrode meters, and we also have combined electrochemical and electrode meters. And of course, they work with our software. The principle of this is that in the absence of oxygen, this dye here, if you excite it with a 620 nanometer red-orange light, it will go into an excited state and revert back to the non-excited state under the emission of fluorescent light. If oxygen is present, that will quench, or so to say, take the energy out of the excited dye, so it will not be emitted as fluorescent light, but will be a non-radiative energy transfer. And the more oxygen that is present, the less fluorescence is emitted. This fluorescent dye can be, for the fiber types, the 50 micrometer and 430 micrometer fiber. They are placed on the tip of the fiber, embedded in a polymer. On the 3mm diameter steel tube, it's placed in the opening of the steel tube here. So it's a very handy sensor, very robust and very easy to use. So the excitation of the dye here occurs, is done by the optical meter. There's a photodiode that emits light, goes through this half-transparent mirror, through the optical fiber out to the dye. The fluorescence is then transmitted back, reflected by the mirror and measured by a photodiode. So when you excite the dye with light, here's light intensity, a very short light pulse, then the fluorescence comes up, and then when you turn the light off, the fluorescence dies away again. That is in the absence of oxygen. If there's oxygen present, then fluorescence doesn't get as intense, but it also dies out faster. And this lifetime of the dye or the fluorescence is actually what is utilized for measuring oxygen concentration, because this is not dependent on the amount of dye present on the fiber. This would the absolute intensity will depend on the amount of dye, but the relative decrease here will not depend on the amount. The way it is done by the optical meter is that it sends out modulated light at a frequency of 4 kilohertz. So it sends short light pulses of 10 milliseconds, so with 40 periods like this. This is the red. The fluorescent light that comes back in the absence of oxygen, this is the one here. See, the peak comes back later than it was emitted. That makes sense. It takes time for the fluorescence to be created and to die out again, and the intensity is also lower. But when there's a lot of oxygen around, then the intensity is even lower. But because the intensity dies, or the fluorescence dies out much faster, then the peak of this waveform here is less delayed as if there was no oxygen than if there was no oxygen. And the optical meter does a fast Fourier transform of these waves and determines the position of the peaks very accurately, so it can determine the time delay or the time shift between the peaks of the emitted light and the fluorescent light. And that is what is used for measuring the oxygen. So we have two different principles for measuring oxygen. When should you use one instead of the other? Well, they each have their advantages. The oxygen electrode is more stable over time. It's more flexible, the optical fiber, which may not be an advantage, may be a disadvantage if it flexes too much and you don't know where you're measuring. It's not H2S does not interfere with this one. It does a bit with the amperometric sensor. It is has this retractable tip design, and it also has the 3mm mini sensor on this here. The amperometric sensor, that can be made faster. The tip size can be made much smaller than the 50 micrometers of the optode. It has a more rugged design for profiling. So if you profile in sediments with the optode here, the polymer holding the dye will be worn off, and you will lose signal. With an amperometric sensor, the glass sensor, you can measure as many profiles as you want. It's not damaged by that. It can measure over a wider range of concentrations. We can modify the ranges as well, and it has a larger temperature range. It's not flexible, which may be seen as an advantage if you want to know exactly where you are and not have a sensor that is bending a bit. And then it comes also in needle versions where we can fill the space between the sensor and the needle with glue so that gases cannot pass through the needle. That's not possible in this version here. I already show you this. I'll just get down to these are all our standard products, but we can do a lot of customizations on top of that. So we can make sensors with different lengths and diameters than those that are standards. We can change the behavior of them, change the response time, the sensitivity to steering, and also the concentration range. So low range or high range sensor. So the tip size is important, of course. We have many different tip sizes. First of all, if you have a small tip size, you will get a higher profile resolution and you will get less sample disturbance. Also get faster response. The only disadvantage is that it is more fragile. But there are other effects of the tip size that will affect the profiles actually. So this is to compare here as profiles with measured with a small and with a big sensor. And this is profile measured by the small sensor. This shows the water above the sediment. This is the diffusive boundary layer, and this here is the sediment that we are measuring into. The diffusive boundary layer is a layer of stagnant water that sticks to the surface of the sediment due to friction, and which is stagnant, and only oxygen is only transported, or solutes in general, only transported by diffusion through this layer. That is seen here as this linear change in concentration. So with a very small sensor, you can see then we are measuring the concentration of oxygen right in front of the tip of the sensor. And the supply of oxygen here, in this case, can come from a whole sphere. So there's a spherical supply of oxygen to the sensor. Only a very small part of the sphere is blocked by the sensor. If you use the big sensor, you will block half of the diffusion sphere, and you will change the supply of oxygen to this sediment in front of the sensor. That means that after introducing the sensor, the supply will be lower, and then the signal will adapt, or the concentration will adapt to the lower supply and find a new steady state concentration, which is lower than the previous one. And therefore, you might risk getting a profile that looks different from the ideal profile. Another way of looking at this is that when you have a small sensor, then oxygen can easily get down to in front of the tip, whereas if you have the large sensor, there's a longer way of diffusion into the segment in front of the tip. So the effect of the sensors is that you don't affect the oxygen supply here, and you get a fast stabilization. Here you affect you reduce the supply of oxygen, and therefore you'll get an underestimation, and you may get a drifting signal. I'll illustrate this here. Now, let's say we are measuring a profile. We are this is the concentration, and this is over time. Such an arrow indicates that we have moved the sensor one step down towards the sediment. Here we reach the diffusive boundary layer, and oxygen starts to decrease. But for each of these steps, if we look in detail, you can see that there's a fast decrease in the beginning, and then it becomes flat and reaches a plateau. And that means that the sensor has responded, and that it's just measuring the concentration that was in the sediment before we inserted the sensor. If we insert a big sensor, you will see a different type of profile, because if you look at these, they don't reach the plateau, they just keep decreasing. And this is because the sensor will block access, part of the access of oxygen to the sediment in front of the sensor, and this will take a little while before you have a new steady state here. So you will see this as a drifting sensor, a very slow responding sensor if this is a problem. Other effect of the tip size is that it affects the diffusive boundary layer. So there's turbulence in the water above the diffusive boundary layer. If you introduce an object like a sensor, it will affect the turbulence and erode the diffusive boundary layer a little bit. If you introduce a big sensor, then this erosion will be bigger, and the effect on the profile will be you will have a thinner diffusive boundary layer, and you will affect the oxygen concentrations in the sediment somehow. So there are interferences with some of the sensors. As I mentioned, sulfide will interfere with the oxygen sensor, the light will interfere with the H2S type, hydrogen with the sulf sensor, NO with the N2O sensor, and H2S with the hydrogen sensor. And if you go to our webpage and look at these sensors, you will see the interferences that we are aware of. They are listed there. And if you experience other interferences, we'll of course like to know, so we can put it there. As I mentioned, signal is very low. That means that we're measuring in the 10 to the minus 12 amps range. So grounding is important. You should use a good quality of electricity for your amplifiers, and you can ground your setup. For some sensors, it's required. Then the sensor is labeled, just such as the NO sensor. What you do is that this cable is inserted into the ground receptacle here, and you dip the tip into your setup. That can remove a lot of external electrical noise. We also use a coaxial design for cable and sensors. So in a coaxial design, there is a center conductor here that is protected by first a layer of aluminum foil and then a metal mesh here, which is all connected to the ground. That prevents external electrical noise from getting into the conductor. The same is carried on all the way out through the sensor, because the reference electrode is connected to the ground here, and because the electrolyte is electrically conducting, it acts as a shield, just like as the metal shields here. So the sensor signal all the way from the tip all the way into the amplifier, it runs protected inside this coaxial. Calibration of sensors, that's of course important. If possible, you should always calibrate at same temperature and same salinity as you measure. As I mentioned, the sensors for gases, they are linear, so you can do a 2-point calibration, one known concentration and a 0 concentration. For an oxygen sensor, that would be the anoxic or the 0 calibration would typically be an ascorbate solution, which we have in our calibration kits, or you could do use N2 gas as well. The air saturated or the known concentration would typically be air saturated water. That would, in our calibration chamber here with a small atmospheric air pump, you can get air saturated water. If you know the temperature and the salinity, then you can look the calibration concentration up in a table. And this table is built into the software, so you only need to tell the software what the temperature and salinity is, and it will calculate the concentration. So I'll show some examples of calibrations. So the sensors respond to the partial pressure and not the concentration as such. Henry's law says that concentration equals the solubility times the partial pressure, and therefore partial pressure equals the concentration divided by the solubility. This means that if we keep solubility constant, that means we will keep temperature and salinity constant, then a change in partial pressure will equal a change in concentration. That's why a sensor that is measuring partial pressure can be used to measure concentration, actually. If concentration, on the other hand, is constant and you change solubility, then you'll change the partial pressure and you'll change the sensor signal. I'll show you a couple of examples of that where we vary the salinity. In the first example, we keep bubbling with air in the calibration chamber, and then we add salt to obtain 6 different salinities, as you see here, up to full seawater salinity from fresh water. Now, when we are bubbling, we are continuously equilibrating the water with air, and that means we are maintaining the partial pressure in the water to be the same as in the air. And this is why we get the same sensor signal for different salinities. So that means the partial pressure is constant, but since the salinities are different, then the concentration is actually different for these different salinities. The other way to do it is that you dilute a stock solution into a beaker with a known amount of water. And if you do that at different salinities, as shown here, 6 different again up to full seawater salinity, then you get a difference in sensor signal. The reason for this is that, well, we have the same concentration, but we have different salinities, and that means that we change the solubility. So, and when salinity goes up, then the solubility goes down, and then the partial pressure will go up. And the reason of this is called Henry's law, that if you lower the solubility, you keep the concentration constant, then the partial pressure will be higher. And since the sensor responds to partial pressure, you will have a higher signal. As I've shown a number of times, all the sensors are sensitive to temperature, so they will give an increasing signal with temperature, mainly from when they are measuring. The zero will only vary a little bit with temperature. We can do a automatic correction for changes in temperature in the Uniamp series of instruments. And we do the calculation when we convert a sensor signal to a concentration in 2 steps. First, we convert the sensor signal to a partial pressure, and then the partial pressure is converted to a concentration. The temperature affects both of these processes. The first one is called the sensor response. So this is the electrochemical and diffusive effects on the sensors. And the solubility effect is the second. That is because the concentration, or the ratio between partial pressure and concentration, that changes with salinity and temperature. So what you actually do when you do a calibration, that is you establish a relationship between the sensor signal and the partial pressure. You can later then use the partial pressure and convert that into a concentration. For example, if you measure 110 millivolts here, you'll convert that in this case to about 110 millimeter mercury. You can then convert that to a concentration of about 200 micromolar here. So this is the sensor response, and this is the solubility effect. This here depends on both salinity and temperature, and that is known from the literature. So there are tabulated values, and that is built into the software. That's how the conversion is made. And this relation is established by calibration. To do that in the software is very simple. We have these 2 checkboxes, so you can decide whether you want one or the other or both of these temperature compensations enabled. And you can enter your temperature manually here, or you can, as in this case, choose a temperature sensor to give the temperature input. And this will work within plus minus 3 degrees of the calibration temperature. Well, at least it will work. It will work well within that range. It will also work outside, but the precision will be lower. So about the last one, sorry, I'm running a little over time. That is about signal drift. So an ideal sensor would look like this. So you have exactly the same signal over time. This is over 30 days. It's not so often we get that. Often there's a little loss in signal over time. It may be linear, or it may have a different shape. We don't quite know, and it depends on the individual sensor, since they are handmade. So they are very individualistic. But the drift is so low that it's not a problem at all. You just need to calibrate now and then, especially if you're working in profiles or whatever. You are working within a few hours, and this is here we're talking a month or so. So it's not any problem at all. It's just something you should be aware of and do calibrations. Another type of drift you may see is that if you give the sensor a physical shock and don't break it, then you may see shift in signal, a jump. And the reason for this is that if the cathode or working electrode inside the sensor moves a little bit after such a physical shock. If it moves away, then it will give a lower signal for the same partial pressure. If it moves forward towards the membrane, towards the outside, then it will give a faster and a higher signal. So recommendations for calibration, well, calibrate at same temperature and salinity if you can, or you can utilize the uniamp temperature compensation within a few degrees from the calibration temperature. Be careful with the zero definition or the baseline, especially if you're working at very low concentrations, then you may need to calibrate now and then. Always calibrate before you do your work, because first of all, you know that the sensor works well. And second, if you manage to break the sensor during your measurements, then you get results until the sensor breaks. Calibrate often to avoid problems with signal drift and signal jumps. And this is the final slide. I just want to advertise our so-called Unisense Academy. You can see this is links to our website, where we have a lot of useful information. See, this is more or less what I have said today. Well, more detailed, some of it about amperometric, potentiometric sensors. There's a web lecture. We have about the sensor types, the meters and amplifiers. Then we have for the different sensors a more detailed explanation of how they actually work. So you can go in here and have a look, and you're always welcome to get in touch with us, send us a mail, or use the buttons on the website, and we will be happy to help you. And now I would like to answer any questions you may have. Yeah, please. Yeah.
Can I start? I don't know.
Yes, please go
if
ahead.
Someone else.
Hi.
Okay, it's not really a question, but I was curious because there are some rumors, let's say, that a CO2 sensor could be available at some point. Is it true? Is it correct? Or is it too challenging to prepare a CO2 sensor?
Well, it depends on how you define this at one point, because there is a sensor that has been developed at Aarhus University and it works. It has been used for a couple of publications. It's not anything we can produce and sell at the moment, at least. It's too short-lived and too unstable. So it works for those people that can produce it in the lab and use it immediately and make a new one when it after 2 hours doesn't work anymore. So it's not anything we can we want to sell at the moment. But we are of course keeping an eye on it, and we know the people behind it. So yeah, but it's not going to be this year, or maybe not next year. I don't know. Sometime in the future. One problem is also it's really slow responding. I think they have changed that a bit. So yeah, but basically it's a pH sensor that is where CO2 gets in and changes the pH in a small volume of buffer where a pH electrode is sitting, and it takes time for this equilibrium to establish. And, yeah.
Okay, because it was interesting to think about a CO2 sensor that can also penetrate tissues like an oxygen or hydrogen, whatever sensor, compared to the pH sensor that maybe is more delicate.
Yeah, would be really nice. And as soon as we have an idea that it's possible, then we will of course produce it. But,
thank you.
Yeah, you're welcome.
Okay, so we have two other raised hands today. I think the first one was Ketil.
Yeah. Okay.
Yeah. From you. Hi.
Hi. So I was wondering about the temperature compensation. If you have a sediment and you want to measure oxygen, but at the same time as you have an oxygen gradient in the sediment, you also have a temperature gradient. Do you have a profiling temperature sensor that you can use at the same time, or how do you do that?
Yeah, we do. Yeah, we have a 200 micrometer. I think it's the thinnest one, and a 500 micrometer as well. So you can do that, yes, and then it will correct for that. Yeah.
Thank you.
And then you can use this. We have a 2 sensor holder for the micro manipulators. You can place them, the tips very close together, and then you can get it at the same time.
Good.
Yeah.
Thanks.
Yeah. Then we have Olivier with a raised hand.
Hello. Thank you.
Hi. Hey.
Hi.
Hi.
I'm sorry. There's something. Can you go again about what factors play the most or influence the most the rapidity of the response of the sensors? You talked about the tip size for sensitivity, but in terms of reading the getting a reading rapidly and measuring continuously, how do you adjust that to?
It's simply a matter of the distance from the front of the silicone rubber membrane into the cathode or the working electrode. So the average diffusion time for a molecule depends on the square of the distance. So if you double the distance between the front of the sensor and where, for example, oxygen is being reduced, then you will get 4 times as long response time. So very fast sensors, they have a very short membrane so that the cathode is very far out and close to the front of the sensor.
And that plays on the the main reason to have the cathode far away from the tip of the sensor is.
Well, then if you have if you place the cathode very close and it will have a very thin membrane, then you have a very high flux of oxygen or solute into the sensor. That gives a larger consumption of the solute, and therefore it becomes more sensitive to steering. So there are all these trade-offs. So if you make a very fast sensor, it's probably more sensitive to steering. You can then make it wider, and you can, there are many different trade-offs.
The same scope. When you were talking about the fragility of the tip, but basically this can be easily. So it seems it's much better if it's smaller because you have a lot of advantages, but it's more fragile. But I guess this is not a problem anymore if the tip itself if the sensor is in a flow. If it's for lab experiment, in a flow through cells, then there's no disadvantage to having a small tip, right?
No, it's typically a 500 micrometer sensor we mount in the flow cells because that doesn't matter. There's a continuous flow, and that's fine. The only thing is if you, that should not be a problem. It's we almost always mount the thick ones. Now and then people want very fast ones, and then we mount one of the very fast responding one with a short membrane and a thinner tip and so. But normally it's just a standard 500 micrometer one.
Thank you.
Okay, we have one more raised hand. It's right. Sorry if I don't say it the right way.
Yes. Well, thank you very much. Yeah. Well, thank you. Yeah. Thank you very much for this very nice, interesting presentation, which is made easy for non-specialists. So, well done. Good job. I have a couple of small questions. Question number one is related to the sulfide sensor, which you mentioned might be quite sensitive to H2. So is there any quick way of knowing whether H2 is a problem in my sediment or in my mass? I mean, how can I check that? I mean, if I don't have an H2 sensor.
Yeah, well, check the literature as a start, I would say, to see if it could be expected. I've been a bit surprised to see that many of these microbial match studies that have used hydrogen sensors have actually found hydrogen in significant concentrations. So that is could be a warning that you should think of it. But otherwise, it would be interesting to know the concentration of hydrogen, I think, and measure with a hydrogen sensor.
Okay.
Yeah, but I don't have any other.
Good. And the other question is related to the oxygen sensor. Is there any difference between the oxygen sensors that we use for respiration measurements and for photosynthesis measurements? Like if I want to measure photosynthesis, is there any special criteria that I have to watch out for the oxygen sensor?
Yeah, it has to be fast if you want to use the light dark shift technique. Yeah, and I will mention that in the presentation after this, how that is used. And there the sensor needs to be very fast. We use these that have a response time of less than 0.3 seconds for that, because it has to react very fast.
Okay, good. Yeah. Well, my last one, if I may,
sure.
for measuring the sulfide, if for whatever reason I don't have a pH microsensor, Is it good enough to report the H2S signals and changes in the H2S signal, or I do really have to report the total sulfide and have a pH measurements to correlate to?
Well, I think it depends on the reviewer, of course, but it depends also on in some sediments you will not have a strong pH gradient. In other sediments and biofilms you will have. For example, in a photosynthetic biofilm, you may have a gradient where there's a change of 2 or 3 pH units over just less than a millimeter, and there will be difficult, to make a rough calculations. Otherwise, in a heterotrophic sediment with not too much activity, I think the pH will be more or less the same all the way down, and you could make a slurry or whatever, put a macro electrode in and see what is this pH, and then use that for the calculation. Or you could simply just report the H2S and say this is what we have, and then argue that it's similar to some total sulfide concentration.
Yeah. Thank you very much. Thanks.
Welcome. Yeah. Okay, there are some.
Yeah, we have some chat questions.
How can I convert millivolt to kilopascal? Salinity is 0. That depends on your calibration, of course. The software will do that for you if you have done a calibration. Otherwise, it's not easy to do. Can opto technology be modified for measuring other, such as algal toxins? Possibly, I would say, but I have no idea how to do it, and we only have the one. I know some have also a pH that apparently also works, but apart from that, I'm not aware of any. Can I also put a microsensor horizontally into the sediment? Yes, you can. If you go through, for example, a drill hole in the side of a sediment core, you can go horizontally. You should, if you want to point the tip upwards, you should tell us before you buy the sensor, because if you do that, then this little bubble that will always be present in the electrolyte will float up and sit up in the tip, and that will cut the electrical connection inside the sensor, and then it will not really work. We can then, if we know that, then we can fill the electrolyte with a gel, agarose, so that the bubble cannot move into this to the small parts of the sensor. What is your estimated time to experience a signal drift? So will I need to calibrate my sensor midway for a 60-day measurement? Yes, you certainly do, and also more often than that. I think it depends a bit. I think the most stable one we have is probably the nitrous oxide sensor. We sell that for wastewater treatment plants, and it's okay there to calibrate every second month. So that will be every 60 days, so to say. But an oxygen microsensor, you should calibrate it more often. Every day, every few days, that depends a little bit. So our sensors are optimized for response time and for being small, so high resolution, and not for being very stable over time. Yeah.
So we have a raised hand.
Yeah, Victoria.
Please go ahead.
Yeah.
Hello, thank you very much for your presentation.
You're welcome.
The question about kilopascal was mine.
Yes.
I measure a plant tissue, and I know that there is this coefficient in Harrow's law about it depends on a solute and a solvent. And how can I convert these millivolts to kilopascal or millimeters mercury, considering that I'm measuring a plant tissue?
Yeah, well, if you have a calibration, then you know that if you've calibrated in atmospheric air, you know the partial pressure in atmospheric air. And then you can use that to recalculate your millivolt signal into partial pressure. But I think maybe it's easier if you write me with this. If you have a file, then I can maybe have a look at it, and if you send me an email, I think that would be easier.
Yeah, so in just a comment, so in the software we have the unit millimeter mercury, and if you use that for your calibration, you could then convert that to kilopascal afterwards.
All right, but I have to consider that in my plant I have an atmospheric oxygen. Like not that, for example, like in water, the oxygen is different, but in a plant, it's the same as in air, right?
No, not necessarily. It depends on if the plant is producing or consuming oxygen, then the oxygen concentration inside the plant will be different from that in air. But there will still be the same relation between partial pressure and sensor signal as at your calibration. So this is why the calibration is important.
All right. So, okay, thanks. So thank you very much.
But you're welcome to send an email, then I can maybe help a bit more. Yeah.
Thanks.
Okay. And in the near future, we will have converter on our website. It's not implemented yet, but the idea is you'll be able to convert between any type of concentration and partial pressures. So I think that would be very useful, but the software guys are working on it at the moment. So I'm not sure when it will be in, but in a few weeks, I think it will be. Yeah. Okay, I think we need to stop here because the next presentation is supposed to start in 3 minutes. Okay, thank you very much for attending.